Okay, so let's begin the lecture. So so last time, remember, we defined last time we defined we defined u in h minus alpha of m prime e, where m prime is a compact manifold without boundary with, say, partial m prime empty, and E is some Hermitian bundle over m prime. To be the elements, so these are the U in D prime M prime E, satisfying H minus alpha norm. So this is the definition of the norm. This is where we take a U in H alpha 0. So of course H alpha 0 in our case is equal to H alpha, but I keep writing H alpha 0 because in more general context that's the right, sorry, this is the V, that's the right thing to look at. Divided by V H alpha. Elements that are finite. And so the point is we want to understand now, so where we left off last time was to try and understand this norm. Okay, so understand norm from an operator point of view. Right? It's always helpful to see things from an operator theoretic point of view. Okay. So we need a few facts here which we will rectify in time to come. Okay, so I'm just going to state them here now and move on, but we can talk about them, the details of why they're true later on. So the first fact is that this operator, so this is the Laplacian, so any Laplacian, right? So take some connection on E, we have a Laplacian associated with it. And by this, I'm really writing the closed version, right? So because we have a manifold without boundary, there's only one extension of this, right? It has a unique extension. And this is non-neg. And what that tells us now is that the fractional powers are also non-neg. Okay? And this actually allows us to assert that I plus, so we'll see the reason for this later, that this is invertible. Okay, so we see this later. So remember what it means for an operator to be invertible. It means that 1 plus Laplace alpha has dense range and 1 plus alpha u is there's some constant, and there exists some constant, say that depends on the alpha, so we have such an inequality. Okay. So what does that tell us? So because it has dense range and it satisfies such an estimate, okay, so I should say it's injective. I forgot to say that it's injective, right? So the kernel of 1 plus alpha is 0. It has dense range and this inequality is satisfied. So in particular, it means that its inverse has a unique bounded extension. So we denote it by the same thing. But what's really important, yes? Yes, you're right. So the question was, doesn't injectivity follow from this inequality? That's true. So, okay, so I should just say this implies injective. Okay, sorry, yes. That's of course true. All right, so we have an injective operator which has dense range. So it has a unique bounded inverse. But what's really important is not that fact, but what's really important is the following fact, that in this case, the H alpha norm, and remember the H alpha norm is comparable to u plus Laplace alpha of u. So we've already written this before. So this norm is actually now comparable to 1 plus alpha of u. Okay, so what I really want to do is to absorb this lower order term here. So this typically this is typically there to kill the kernel, right? And I want to absorb it into the operator itself because this makes calculations easier. This is something that's always this is a useful little trick to remember. Okay. So another fact. So there's two facts. So the first thing is this. Oops. The second fact is that C infinity M E prime, which is of course equal to C infinity C C M prime because, sorry, this is M prime E, because we're compact. So this is dense in the topology of distributions. Okay. So anyway, so here it's the L2 norm. It can only be one norm. The L2 operators. Okay. So anyway, so let's fix now a u in C infinity M prime E. So in particular, this is also in L2 of M prime E. Okay. Then let's explore what the H alpha norm is. So the H alpha, it's H minus alpha norm here. So this is going to be the sup over the V in H alpha. And now the action of U on V is simply the inner product. Okay. V H alpha. Okay. So now the point is that I'm going to write here. So I have that, I said here that there is a unique bounded inverse for this operator. So let me write 1 plus alpha inverse of u. And now I'm going to write 1 plus alpha v. Okay, so I can do this because I know that the domain of Laplace to the alpha is the same as the domain of I plus Laplace to the alpha with comparable norms. So I can certainly write this. And well, actually, let me use sim equal here, right? And now I'm going to write the norm here as 1 plus alpha of v L2. Okay, I can do that. Good. So now this operator is invertible, so I can consider its extension. So let me write w equals to 1 plus alpha of v. So this is now an object in L2, right? So this means that this inequality I can write instead as the sup of w in L2 1 plus alpha inverse u w, and now again this is w in L2. Okay? But what is this? Well, this is precisely equivalent to the norm 1 plus alpha inverse of u in L2. So it is what we expect it to be in some sense, right? The H minus alpha space, at least on a nice dense subspace, is really the inverse of the operator. Okay, it's somehow the domain of the inverse of the operator, but it's not the L2 domain. It's really the domain in the space of distributions. Okay, so we need a fact that we need to know C infinity M prime E is dense in H minus alpha. So certainly this is true, but we won't prove it. And what that allows us to then write is it means that we can extend this as an operator now from H minus alpha M prime E to L2 M prime E. Okay, so note that L2 of M prime E is contained in H minus alpha M prime E. Okay, so the reason for that is because if we take an L2 function, if we take some section in L2, I mean, we can do the exact thing that I did here, because my V is always in H alpha if U is in L2. So here I could have replaced the C infinity M prime E with just something in L2 and I would have arrived at the same conclusion. Okay, so L2 is certainly an object that sits in H minus alpha. Okay, so this is how we can understand these negative order Sobolev spaces. Okay, so I'll end with a proposition that's probably obvious now. H alpha H minus alpha is a reflexive perfect pairing with the perfect pairing induced by the inner product on L2. So the reflexivity, well, this is so the question is, what is squiggly arrow? So in LaTeX this is / leads to. I don't really care. I mean, I'm just trying to say that we need to know that this is dense in H minus alpha, and that leads to the fact that this is an operator which is bounded from H minus alpha to L2. Okay. Okay, sorry. So now we have I mean, so this is also really, I just want to emphasize, this is also why I really emphasized earlier talking about perfect pairings, because of course the space H alpha, so maybe I'll write that as a remark. Let me just finish this sentence now. So reflexivity of H alpha precisely means that this H minus alpha now, M E prime, is Banach space isomorphic to H alpha dual space. Okay? So I just want to remark that the natural inner product, or the canonical inner product on H alpha, I should say a natural inner product on H alpha is, for instance, given by Laplace alpha U, Laplace alpha V, right? So this is a natural inner product on H alpha. But this is not the interesting inner product for us. Okay, so it's not the interest, well, I shouldn't say inner product, it's not the inner product or the pairing that really comes from the underlying L2 theory, right? So this is also why I said earlier that even if we're just confining our attention to the Hilbert space context, the reason we really need to examine perfect pairings is precisely because we want the perfect pairs that sit at the heart of whatever we're doing to really agree with L2 on dense subsets. Okay, so the L2 is somehow the primary space, and we want things to be induced from L2. So the geometry of our problems are really contained in L2, and then once we fix that, the kind of perfect pairings that we end up getting, as we see here, are really not the natural inner products that we get on the space H alpha itself, but rather it is a pairing where we need to consider some other space, and this space, of course, is isomorphic to the dual space of the spaces we consider. But of course, the dual spaces by the Hilbert nature are isomorphic again back to the original space. But that's not where the interesting information is really living, right? Here we don't care that there exists an isomorphism. What we really care about is what are the isomorphisms. Okay, so now that I've said all of that, we are now finally able to talk about boundary value problems again. Okay, so theorem. Let M be, well, maybe I should write back to boundary value problems here as a back to BVPs, or I should say boundary conditions. Okay, so we have a compact manifold with boundary, right? With boundary, say, with and we have an operator which is an nth order operator that is elliptic. Okay, so that's really important for everything. Fix T to be an inward pointing vector field along the boundary, and recall gamma C of U gamma C is the map that takes us from C infinity C of the manifold into E, landing us in, well, maybe I should recall this outside of the theorem. So this lands us now in what? So J equals 0 to M minus 1 C infinity on the boundary. Okay, so this map is given by U equals to U restricted to M partial T of U restricted to M dot 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 partial T M minus U restricted to M. Okay, so this was this map. So recall this map. This extends uniquely to a map gamma from DOM Dmax now. So we're having our wishes fulfilled to a bounded map, I should say, to a bounded map. And what are the spaces here? J equals 0 to M minus 1, H minus a half minus J. So this is why we require these Sobolev spaces of negative order. Okay, so when we go to the boundary, we're no longer in spaces of functions. We're really in the space of distributions. So a bounded map with dense range. Moreover, kernel of gamma is precisely DOM dmin. So this is really for general order. It's for compact manifolds with boundary. It's for general order. We're not going to prove this. I'm just saying this to you because, I mean, I should tell you what the general picture is. We're going to move on to just concentrate on first order problems. And in the first order case, we will do all of this in detail, but I just want to really state this in the general order case, and you can go look this up if you're interested. Okay, so, all right. So, yes? Sorry, beg your pardon? Precisely. Mm-hmm. Well, I mean, why do I need to use a connection there? I can just take a curve that generates t, compose with u, differentiate, and then evaluate at the boundary. No, because t is a global vector field along the boundary. Well, I mean, if I'm given a vector field, I can talk about... you mean because I'm taking this this derivative in the components of the bundle. That's true, but okay, I mean, you can do this in a trivialization or something and you end up with a consistent object because your vector field T is along the entire boundary of M, right? And you have a Collar neighborhood theorem that allows you to deform the neighborhood, a neighborhood of the boundary globally. Yes, if you like, sure. I mean, the problem with differentiation is that it becomes a problem if you don't have a direction which is global, right? I mean, if you give me a vector field, I mean, sure, you need to make a choice of a connection in some sense, but regardless of what connection we choose, I mean, the partial t is a globally defined direction, so it's not really problematic to make sense of this. At the end of the day, look, I mean, you're right, there are some technicalities that I'm brushing under the carpet here. But the point is that for our purposes, all of this will go away, right? Because for first order problems, when m is equal to 1, we only have the boundary trace without any derivatives to deal with. There are some things I'm brushing under the carpet here. That's true. Absolutely not. It's minus j. The point is you won't get plus, right? In general, I mean, as you've taken derivatives of u, you're going down in the Sobolev scale. The point is that for boundary value problems, you leave elliptic regularity, right? That's why it becomes hard. So for instance, if you're a first order operator, you will end up in h minus a half, not in h a half. If you're in the Sobolev space h1, then certainly you'll end up in h a half, right? This is what we looked at last time. So that's a very important point. This is also the connection somehow between boundary value problems and non-smooth geometric problems, because on certain scales, for boundary value problems, you have to really end up treating it as if you're in a non-smooth world. Okay, so thanks for those questions. Okay, so let me just sort of brush some of these things under the carpet for the moment, because all I want to really say here is that this accomplishes what we want, right? So accomplishes, yes, but just one second. I'm just gonna say this. Accomplishes what we want for M compact, i.e. We have H check of D, which is equal to gamma acting on DOM D max, which is how we defined it before. And now we can make sense of this, right? So we know that this is densely contained in some spaces. I mean, okay, they might not be function spaces, but they're still distributions. So we can still understand them. And so first of all, they're densely contained. And that means we can topologize such that it is isomorphic to DOM D max mod our DOM D min, because we also have information about the kernel of this. Okay? But the upshot here, so the upshot is H check of D is no longer abstract, right? Of course, we still haven't really done anything, right? All we're still doing is we're bringing the problem that's on the interior to the boundary. So the interior operators, we're bringing it to the boundary, but at least know where where this check space is contained. So sorry, there was a question before. No, the operator D doesn't. I mean, what do you mean? So where the operator D appears is, I mean, here you're making a statement that this is a bounded map. So this is a bounded map from the Banach space DOM D max. So the operator certainly appears there, right? You need to know that, you know, gamma of U norm is controlled by, you know, U in the operator norm induced by, or the graph norm induced by D. So that's the place where the operator appears, right? Yes, that's right. Yes. Yes, we can consider all of these partial derivatives and restrict them to the boundary. I mean, of course, the way we have to make sense is through an extension, right? So here, of course, I mean, because I'm on a compact manifold, I'm using the fact that and everything is smooth, our geometry is smooth, and a functional analytic way of seeing it is exactly that: compactly supported smooth sections of this sort, right? So things, not things that are contained in the interior. Of course, I can replace this with C infinity M of E, right? Because we're in a compact manifold. And what it's saying is, I mean, we know that C infinity M of E is dense in the maximal domain. And so, you know, the way that we make sense of this extension map is precisely through an approximation, right? If you now take an element in DOM D max, we have a sequence in compactly supported smooth or smooth maps or smooth sections that approximate an element in DOM D max, and then we can use that approximation to define the gamma C, and then we know that this extends uniquely to a bounded map. Yes. Okay. Okay, so this is the upshot. Okay, we would desire potentially, we would potentially desire M non-compact So certainly if we were to do that, one thing we would require, one condition we would require is that C infinity C of ME is dense in DOM D max. Okay, so this is also already a condition that we've seen, and we would use the Collar neighborhood theorem. Okay, so what does the Collar neighborhood theorem say? So it says that there exists a neighborhood U in M with the boundary in U. U is open and U is diffeomorphic now to 0, 1 cross the boundary, right? So, so it's saying that we have some boundary. So I should say here that I'll emphasize here, M is non-compact, but the boundary should be compact still, right? So M is non-compact, but of course we should still have the boundary being compact. So this would be like an exterior region problem, right? So what it's saying is that we have some neighborhood here, and then we would go into some cylinder. Okay, so this is not a metric deformation. This is purely topological, right? So once you have something like this, you would you could take chi equals to 1, so you can institute a cutoff. So institute cutoff chi. So this is going to be a smooth function on ME such that which is also in L2, so I should say smooth intersect L2 of ME such that, so chi would be equal to 1 inside U, say, support of the okay, so I should say that the support of D of psi would be compact, and then you would use this to so let U be in DOM D max, then you would have UN in C infinity C of ME with UN converging to U. So then you would instead look at UN equals to 1 minus chi of UN plus chi of UN. And now this is compactly supported near the boundary. So maybe you want to map this into some manifold where you double this, maybe, so you institute 2 boundaries, and then you can do some technical juggling and try and reduce it down to the compact theorem, right? So I'm not going to give details here, but I'm just saying what is possible. So but the point here is really that the trace of this part of the approximation is 0. The boundary trace up to all orders is 0, right? So I won't leave it at that, so I'll just exercise, think about how this can be done. Okay. So let me just also emphasize what we have done so far? Okay, so what have we done so far? That all we've done is we've brought the interior problem, i.e. dom d max mod out dom d min. I shouldn't call this the interior problem. This is the problem that sees the interior to the boundary, i.e. to h check, i.e. h check of d. We've done nothing more than that, right? So what we would like to do now, now we want to dismantle h check of d via boundary data. Okay, that's ideally what we should be able to do, right? So in trying to understand this problem, what we've done is we've used these negative order Sobolev spaces to be able to describe the action of the boundary trace map with, consisting of transversal derivatives up to order m-1. We've brought everything to the boundary, but now we want to unpackage everything, right? We want to understand this is now a Banach space that's sitting purely on the boundary that contains all the information we want about the extensions of operators sitting between dmin and dmax. Okay, so I'm going to go back to the situation where M is compact. For first order problems, we'll think about situations where M is non-compact, but here let's just think about M compact, right? So background assumption, M compact. Yes, question. Yes? Mm-hmm. So this is an order M operator. Very, very good question. So the question was, given two operators of order M, so the maximal domain fluctuates. That certainly moves. The question was, is the domain of the minimal extension the same? So I tried to not really mention anything there to avoid any questions, but since you've asked me, maybe I'll insert it. So that's certainly true. This is HM0 ME. That's always true. Very good. Okay. So background assumption. So getting back to this, M is compact. So far what do we have? So far we have that dom d max, dom d min. I'm gonna repeat this many times because we learn through repetition. So gamma tilde is the induced induced map. So so this is isomorphic. Okay. Now let me define C of D. Okay, or script C of D. Okay, so define. Let me say define. Define C of D to be gamma acting on the kernel of D max. Okay, so you can maybe call this the Hardy space of solutions, if you really want to call it a name, but I'm not going to worry about it too much. So I just want to say here that, of course, we have the kernel of D max. It's not hard to show that for a closed operator, the kernel is also a closed subspace. Also in L2, right? Because, of course, on the kernel, the D max, the graph norm and the L2 norm are equivalent. However, I mean, there's nothing to assert that this space here that I've written, so this is certainly going to be a subspace of H check of D, but we cannot, from this consideration alone, claim that it is a closed subspace, right? Because dom D min is not necessarily contained in kernel of D max. Okay, so we can only make such assertions about the nature of closed subspaces here being equivalent to the nature of closed subspaces here. But this somehow fits outside of that picture. But it is a famous theorem. So for instance, Bob Seeley, who made very many contributions, perhaps it was even known earlier than this, right? So I certainly know it from a paper of Seeley's from 1966, that there exists a projector P of C, right? So P of C on now J equals 0 to M minus 1 H minus a half minus J partial ME onto C of D. Okay, so it is a closed subspace. So we now know that it is a closed subspace of this larger space. Okay, this projection restricts to projection on J equals 0 to M minus 1 H S minus a half minus J, say partial M E, and this is for all S greater than or equal to 0. Okay, so it's a very nice projection. So I'm avoiding now how one concludes this. Actually, this projection is a classical pseudo-differential operator of order 0. And the conclusion that it's bounded on all of these spaces stems from that fact, but I don't want to talk about pseudos here, right? You can find lots of information about pseudos in the literature. Lots of people have done things in this way. This is not the approach that we'll take from here on. And this is why I've carefully avoided talking about pseudos in writing, but it would be irresponsible of me not to mention that this is the traditional way a lot of these things have been done. Yeah. Okay. Moreover, H check of D is equal to 1 minus PC of the space J equals 0 to M minus 1 of H M minus a half minus J partial ME plus P of C now of J equals 0 to M minus 1 of H a half minus J partial ME. And this is precisely C of D. Okay? So let's just take a minute to let's give this a name. Such a projector P of C is called a Calderon projector. Okay, so from what I recall, Bob Seeley was a student of Alfonso Calderon, who was a very famous Argentinian mathematician. who made massive contributions. So in fact, the complex interpolation method that I showed you last time, from what I recall, was also due to Calderon. He made lots of strides in this area. So you'll also come across people talking about the Calderon projector in possibly in the literature, or when you have conversations about this. It's fundamentally wrong to say that, because I mean there are lots of Calderon projectors. The range of every Calderon projector, of course, is fixed, and it's this Hardy space of data of solutions. But the complementary subspace can move. Okay, but the fact is that the complementary subspace is always a higher regularity space, and this relates to the earlier question that was asked. Why is it not m minus a half plus j? Okay, so fundamentally there will be an irregular piece, and this irregular piece means that the domain of D max for boundary value problems, or for boundary value problems outside of dimension 1, right? So where the boundaries are just points. So outside of that situation, the minute you have a one-dimensional boundary, the domain of the maximal operator will no longer be in Hm, despite it being an elliptic operator. Okay, so this is something really that's important to commit to memory, because elliptic regularity tells us that without boundary, the domain of an elliptic differential operator of order m is Hm. But here, when we have boundary, there is a part which pushes it outside of that regularity regime. So it is really non-trivial. Okay? However, this part, it's easy to see, certainly is going to sit in Hm. Okay? Because each of these subspaces relate to where the trace lands us, and I mean we're adding m to the problem here, so all of these are now positive Sobolev spaces. So that's good. Okay, so what does this allow us to do? This decomposition. Okay, so let me write it down. So this allows us to understand the check space of D almost of boundary information alone. Okay? I say almost because we have CD, which are solutions to D max U equals 0, right? So somehow this still sees the maximal operator. So we can further divorce this, right? But it's a non-trivial task. So how might we divorce this whole thing? So how might we divorce this relationship? So one way we could imagine how we could do this is to try and look at a canonical operator. I mean, here we have, remember the collar neighborhood theorem gives us a cylinder. So maybe we can look at a problem on just a cylinder so that we can reduce the problem here to the problem of a cylinder. But that would require us to also move between two different operators, right? So on the cylinder, maybe we have d sil max, and we need to know how to move. So the collar neighborhood theorem is just a topological theorem, right? So we have d max here, and we need to know how to move from the d max to just a canonical operator on the cylinder end, and maybe then maybe we're still then dealing with Calderon space or this Hardy space of solutions on the boundary with respect to some fixed operator. But if this operator is somehow canonical and easy to understand, then we've still managed to detach and deconstruct the space H check D from information more or less on the boundary alone, right? Because so the hope is that this is an operator determined from some operator on the boundary. Okay, so it would be the Holy Grail. Reduce. So I'll write this down just so it's written. D max or considerations of D max to D max some canonical, say, or coming from a cylinder or something, some canonical D max determined by some operator on partial M. How would we do this at the level of general order problems? I have no idea. Maybe these are things that you can think about. Maybe this is already known. I'm not an expert on the general order setting. Yes. No. I mean D max. Okay, sorry. D max is unique, but D max. So the question was, if I have an operator D, is D max not unique? Absolutely, D max is unique. When I said no before, what I mean is now we're changing the operator. This is no longer D. This is D sil or D can. So it's a different operator that's yes. That's always, when I write D something max, I always mean the maximal extension of the operator. It makes no sense to talk about it in any other way, right? We cannot talk about max and then something else. We're talking about an operator and then it determines a maximal extension. So this notation is never ambiguous. So this is like attaching, say, the cylinder. So it's like being able to attach a cylinder to the space itself. But if I attach a cylinder to the space, I'm fundamentally altering the operator. So how do I know that, for instance, if I'm in the maximal domain of this D max, and I do a cutoff, then I'm going to now end up in the maximal domain of another operator, right? So there's an analytic obstruction to being able to do this. And we'll see that we can do this in the first order case. Okay, we'll study that. But at this level of generality, I can't really see how we would do it. It's an interesting question, but I don't know. Okay, so I mean, this is an advanced research level course, so we're going to hit boundaries, no pun intended, as we go along. But okay, anyway, that gives maybe some perspective of how we could think about deconstructing this check space in terms of something very canonical that doesn't really depend on the solutions of the given operator, but maybe some canonical operator, and then maybe we could understand it more precisely. That would be good. I don't know how to do it. Yes. Mm-hmm. Well, the Calderon projector would be if you take the solutions to the equation, Laplace max equals 0, and then you restrict those solutions to the boundary. Well, I mean, in general, it'll land in a very nasty space, right? Because you see, for order 2, the Calderon projector is going to consist of -1/2 and a -1/2 minus 1. Yes? No, that's not true. So the question is, does not elliptic regularity tell us that all the functions should be smooth? That is the case in the absence of boundary. When you have boundary, you can precisely, I mean, the benefit of this splitting of the check space is precisely that you're going to have the domain of the operator moving outside of HM. Okay, so let me just so the question is, what is the Calderon projector in the Laplace-Beltrami case? Well, I mean, I don't know how to cleanly describe it. We will see it for the first order case where, in certain situations at least, we can really understand this in a very concrete way. However, the point is that this is not something like the Neumann condition or whatever. I mean, typically with boundary value problems, specific boundary conditions are considered, and then, of course, these are by construction nice boundary conditions. And then, they are going to certainly sit inside the boundary restrictions by gamma are certainly going to sit inside this Hardy space. However, it's not going to be the totality of this Hardy space. Okay? The full solutions in the maximal domain of the operator are nasty. There's going to be lots and lots of solutions that are going to be very irregular, even if we're in the complete smooth setting. And there's really infinitely many of them. Okay? So let me just define, I mean, we've seen this before, so let me touch upon that also, right? So let me say that so what is a boundary condition? Let's recall a boundary condition, right? Recall, so how did we define a boundary condition? B is a boundary condition if B is a subspace of this check space, is a closed subspace. Okay, so I want to now define three kinds of boundary conditions. So a boundary condition B is called elliptically regular. If B is in addition to, so now, I mean, this check space contains lots of positive order Sobolev spaces. So in addition to being a closed subspace of the check space, we want it to also sit inside J equals 0 to m minus 1 of H m minus a half minus J partial m e. Okay? And so we want this, and we want the adjoint boundary condition. So this is we take the adjoint operator and then we restrict. Okay? We want this to also sit inside H minus a half minus J partial m e. Okay, so you might object and say, well, why do we specify it for both these boundary conditions? Well, I mean, typically, a lot of these problems are studied when you have a self-adjoint extension. And when you have a self-adjoint extension, B, dagger and B are the same. But we're working in a general setting here. So we're not just focusing on self-adjoint boundary conditions. So we really need to control for elliptic regularity, or the notion of elliptic regularity, we should control both things. You can, if only one of the spaces sit in there, you can call it semi-elliptically regular if you like. But let's not touch upon that, right? So example and non-example, I mean, the Calderon projector tells us, it gives us two canonical subspaces, right? So C of D is a closed subspace of H check, and, well, maybe I shouldn't write C of D. Let me write, let me consider B equal to 1 minus PC sum j equals 0 to m minus 1, h m minus a half minus j partial m e. So this is certainly now a closed subspace of the check space. Is certainly closed subspace of the check space. So this is halfway to being, so this is halfway to being elliptically regular. Okay? So if we look at the domain of this operator, certainly we will have that this has elliptic regularity. Okay? So also, I mean, this space, the check space is really fixed. I mean, we have an explicit description of it. So if I take hm, if I take, say, an operator with domain hm, this cannot be a closed operator in this case, right? Because if I take the boundary trace map and I restrict it, I end up with one part here. So this is exactly going to be hm, the gamma acting on hm. So that's going to be this part. But then I'm going to have a part sitting in here which is not closed. So certainly a domain, in boundary value problems, you can only have operators which have domains contained strictly in hm, but not equal to hm and closed simultaneously. Okay, so that's also distinct from the case of no boundary. So what I really wanted to do is to give you a non-elliptic boundary condition. So C of D is what? This is precisely equal to this space, j equals 0 to m minus 1, h negative a half minus j partial m of e. So this is certainly closed by construction in h check of d. So we actually have an operator d of cd. And the domain of d of cd cannot be contained in hm of e. Right? In fact, this space, the dimension of C of D is infinite dimensional, which means that the dimension of the kernel of D max is also infinite dimensional. Okay, so there are lots and lots of nasty solutions. So again, at this level, we can talk about another class of interesting problems, another class of interesting boundary conditions. So a boundary condition B is called Fredholm, or Fridholm for the Swedes amongst us, if dB is a Fredholm operator, i.e. that means that the range of dB is closed and dim k dB plus dim L2 mf mod out range of dB is finite. Okay, and that's of course the index. So we can see actually that, so every elliptically regular, I don't know why I underlined that actually. Boundary, every elliptically regular B is Fredholm. Okay. And I just want to end this discussion of of the results pertaining to this with just this this last proposition, So this is higher boundary regularity. So this is the closest thing that you will get to elliptic regularity, right? So we can characterize the elements of DOM D max that are in HS plus M. And these are precisely going to be the U in DOM D max, obviously, such that D max of U is in HS, ME, and the Calderon projector of the gamma of this U is in HS plus M minus a half on the boundary of okay, sorry, to remove this, okay, minus J, J equal to 0 to M minus 1 of E. Okay, so of course one direction is easy. If you're in HS plus M, then if you act on such a object with an elliptic operator, then of course we're going to end up in HS. This is going to differentiate that section M times. And then we all also know how the trace acts on the Sobolev scales. So we know that the trace is going to land us in the right spaces. And then, of course, it means that the Calderon projection should also land us in those spaces, right? Because this is an operator that restricts, as I said, it restricts to these Sobolev scales when we range from S to positive values. So at least I'd like to get through this example now so someone already mentioned the Laplacian. So let's just have a look at the Laplacian. Okay, so in fact, the only reason I ever mentioned this higher order theory, I would have just kept to the first order, is so I can give you this example, because the second order things seem to be the way that boundary value problems are taught, or boundary problems are considered in education, which I personally disagree with. I think the first order things should come first, but anyway, my 2 cents. So let's take a bounded smooth domain. In Euclidean space. And the Laplacian here, of course, it can be described easily, and then suppose we have some inner normal. Along the boundary. Okay. So what do we have? So we have, remember we have this following integration by parts formula. D Lebesgue minus V nabla U. This is precisely going to be equal to the boundary integral of this boundary term minus the boundary integral of V. Okay, and this is with respect to the Hausdorff measure on the boundary, if you like. Okay, so the Dirichlet problem. Okay, so this is where we specify so typically we specify the domain of the operator. So we write domain of Laplace D is the U in DOM Laplace max, such that the trace is 0. Okay. So what is the corresponding boundary condition, right? So B, the corresponding boundary condition then, so implies that B is equal to gamma DOM d max, gamma dom d, and this is going to be precisely equal to 0. And then I'm going to have the normal derivative of u restricted to the boundary such that u is in dom d max. Okay, so the first thing is that this is a self-adjoint operator, right? Is self-adjoint. So, how do we prove this? So, reading off from this integration by parts formula, so what's going to be the adjoint? So, if we take duv, so this is going to be equal to omega of u d star of v, right? So for v in dom, say d adjoint, right? So this is a symmetric operator. So this is the formal adjoint is itself plus now I'm going to have this term on the boundary n of u v, and this is what we have. But if we have okay, so if we have a v in the domain of the adjoint, then that means that this term has to be 0. It forces this term to be 0, right? So this term is forced to be 0. So we must have, I mean, it cannot be that every partial nu restricted to the boundary is 0. Because if that was the case, then the domain of the operator would also be different, right? So we have some u non-zero, and then from that we can conclude that v must be 0 if that's true. Okay, v on the boundary. I.e., v is in I.e., so v is in dom d Laplace max, and v restricted to the boundary is 0, which means that v is in dom plus d. So it's self-adjoint. Okay. No, the star for me is always the L2 adjoint. The dagger is the formal adjoint, the star is the L2 adjoint, yes. Yeah. The second thing is that we can try and understand the regularity. So the first regularity. So we have nabla d u u, right? So by integration by parts, I have that this is gradient u dot gradient u. And so that means that this is u squared. Okay? So that means that u is in H1. But if u is, so u in dom d max intersect, so this further means that u restricted to the boundary is 0, and that tells us that u is actually in H1 0 of omega. Okay? Now the third thing, so elliptic regularity, right? So what does this regularity tell us? Well, I should say higher order regularity, right? So we have u in dom d. This means that u is in dom d max, and u Laplace du is in L2, and u restricted to the the normal direction of u restricted to the boundary. So this thing is going to be now, so u is, so we already know that u is in H1, so this is going to be H0 in some sense, or L2, and then this is going to be minus a half, right? So the Calderon projector then respects this, so that means that B of D is elliptically regular. So that means that in this case, u is in H2 of omega. Okay, so then we arrive at the usual conclusion, namely that Dom Dirichlet is equal to H2 of H2 intersect H10 of omega. Okay, so typically, I mean, I just want to also stress that, you know, the Dirichlet problem, alternative construction is to say nabla D is the operator associated to the energy ED of UV equal to gradient U dot gradient V for domain of this energy D equal to H10 of omega. Okay? So the reason I just want to mention this is because this is really the passage when you want to consider non-smooth geometric problems. So quite coincidentally, this question was asked from me earlier. So here, this is really the metric. So this is the Euclidean metric, right? Maybe you have a non-smooth. So if you have a non-smooth tensor, metric tensor, you can still write EdGUV equal to G of du dV equivalently with respect to the measure that's induced, and then operator theory with of course UV in H1 of your manifold Mg, and then operator theory will give you the Dirichlet Laplacian, right? You can also consider the Neumann Laplacian, so Neumann, and here you would specify it either with the domain. So this is where you have U in Dom Laplace max such that the normal derivative is 0. Or equivalently, you can consider an energy formulation. So now the energy formulation, I'll write it in general for a manifold because it might be useful for if you're considering these things. Now you're considering the same energy, UV, now in H1 of Mg, right? Not sorry, this was H1 naught. The Dirichlet problem is H1 naught. And this leaves access to non-smooth. And what you need to look at are the first and second representation theorems that's in the book of Cato. Okay, so yes, please. More. How do I know that the normal derivative is well, because I know that this, okay, so that's a good question. So I know this because I'm coming from an elliptic differential operator, and I also know that in addition that U is contained in H1. So there is some, okay, I've brushed this under the carpet. There is some extra work to do to show this. Right? But I mean, the reason that I first computed this to show that U is in H1 naught is that you need to use this fact also when you argue what happens when you take the normal derivative and then you take the trace. Yes. I mean, I just wrote this. So the question is, what I do? What am I doing? So I'm realizing the Dirichlet problem here in terms of the boundary condition in the check space, but I'm writing precisely what it is. Of course, this is not new, right? I think you've probably seen this elsewhere, but this is what it really means in terms of the check space. Yeah. Okay. So I'm at two minds about continuing. So so this is all I will say about the higher order problems. Okay, I'm not going to say anything more. Maybe I could just quickly say that these energy methods, since I have 5 minutes. So these energy methods. So what happens? So the just maybe a quick remark, since I have a few minutes, on energy methods. So if you have, so let E, dom E cross dom E to say C be symmetric form, right? I.e., I'm assuming that it's sesquilinear in the second variable, but it's symmetric when I restrict to real valued things. The dom E in L2 of ME is dense. Okay. And I want to say that dom E with respect to the norm that I'm giving, which is going to be, so let me not screw this up. So this is going to be sorry, I'll put a U in here. U squared L2 plus E U square root is a Banach space. Then what we obtain from this is there exists a unique operator, which I will very poignantly call delta E, self-adjoint. The domain of this operator is contained in dom E. And the square root of this operator is equal to dom E. So positive, I should say non-negative, right? This is non-negative shit. Non-neg self-adjoint, such that E of UV can be written as square root of EU square root of EV. And this is with respect to ME. Okay, so this is the way in which you would induce the Dirichlet or the Neumann problem. In the case maybe you have a non-smooth metric, in the case you have non-smooth boundary, you still can set up a Dirichlet energy with the right Sobolev spaces, and then this allows you using these. So this is, I think, representation theorem 1 and 2 in Cato. So this is a very fundamental result, and this is really what allows also, so this is connecting to divergence form theory, right? So these are divergence form operators, and there's a lot of study about them. It's really beyond the scope of this subject, but since I just had a few minutes, I thought I'll mention it. But maybe I'll leave it there, and from next time onwards, we'll forget general order, and we will purely restrict our attention to first order elliptic operators from here on until the end of the course. Okay, I'll leave it at that. Thank you. Yes, please. if you're taking it into another manifold, then this will not be a linear map, right? So it's not going to be a symmetric form. So you could try and linearize it and then study it. But then you need to also understand how these forms behave, say at maybe LP scales or something, if you want to try and come back to the L2 problem through, I don't know, some sort of fixed point argument or something. I really don't know that picture because it's the nonlinear world. I think that's correct, right? If you have a map from one manifold into the other, then, you know, I mean, the point of having maps or sections of vector bundles is at least fiber-wise you're linear. So everything will be nice and linear. But if you're mapping really from one manifold to another, then I think you're going to be nonlinear. And I don't know what happens in that world. Any other questions? Okay, if not, thank you. And so we'll meet next time and start getting our hands dirty with the first order stuff. Ah, okay. Yeah, one more question. The extension with the cylinders. So how do you want, what do you mean, can I connect that to, so the question was, I have this thing with the cylinders, can I connect it to the Dirichlet problem? How exactly do you mean? Okay, so the question was about the picture that I drew before. So so there I was really talking about the following scenario, right? So what we have so far is H check of D, and this is in relation to, well, I don't want to draw this too much like a cylinder, right? This is in relation maybe to, you know, D on this. So we have some operator D and we have some check space D here, right? The problem is that if we describe the check space and we split it into some complementary subspace plus the solution space given, so this is equal to gamma of the kernel of D, then in some sense we're cheating because we still see the interior problem here on the boundary. So what I was saying is, what might be good, what might be interesting is we know that there is a neighborhood here, and then we can deform this, say, to a cylinder. Now, what I want to do is to have a look at a new operator here, right? So we have some new operator, D new, which is maybe built out of D, but it's governed by what's, I mean, because it's a cylindrical situation, I mean, here we're really looking at, you know, if we have some metrics floating in the background, I mean, this would be some G, and this would be something like dt plus Gn, right? And what would be interesting is if there's some operator, say, A here on the boundary, right? So this is now taking us from boundary E back into boundary. And what would be nice is if A induces D nu. Okay? So how might that happen? Well, I don't know. Maybe this is a order m-1 operator, say. And then maybe what we have is something like D nu is equal to dt plus, or some, I don't know, yeah, so let's say dt plus plus this A. Does that even give us order m+1 problem? I think it does, right? Because this is just differentiating on each cylindrical piece. So suppose this. And then we can describe, and then I can say something like h check of d is actually equal to h check of d nu. So if such an assertion can be made, then I am able to really understand and dismantle this check space on a more complicated geometry in terms of the check space of something that is much, much simpler, right? So if this was possible, this would give a more detailed understanding of this check space, divorcing it from having to consider solutions to maybe some complicated problem here, and instead to a much more simpler problem where all the solutions can be understood because it's just a cylindrical situation. Okay, so that's all I was saying. How I could relate this to the Dirichlet problem, I mean, yeah, in some sense that's true, because in the Dirichlet problem here, what I've done is I've described the domain of this, at least of this extension, in terms of H2 and H1 naught. And of course, this is now independent of the operator D. So certainly the Dirichlet problem in some sense could be understood, at least the domain of the operator could be understood in terms of maybe a more canonical operator which doesn't rely on the operator Laplace D, and this is certainly would be the case if you look at this alternative construction, right? If you look at this alternative construction, of course you're picking out elements of the maximal domain, but somehow you have a background space which is fixed, which is H1 naught. So if you now have a smooth metric, regardless of the metric, the domain of the operator is fixed. It's fixed to be H2 intersect H1 0. So I hope that answers your question. No, and describing the full check space even in the second order case is not easy. I mean, in the first order case, we'll see what it looks like. No, because I mean the thing is there are two aspects here, right? When we attach, say, a cylinder, what we're really doing is there are two things. So the first thing is that on a manifold with boundary, regardless of whether the boundary is compact or not, we always have a Collar neighborhood theorem. So a neighborhood of the boundary will be, it will be diffeomorphic now to a cylinder. But that's just a topological condition. Then, we have a geometric condition. So we're not really dealing with the situation of metrics and so on and so forth in our setup, because we just have a measure in our setup. So even with compact boundary, what can happen is that when we go from here to here, we need to know how we can. So if we cut off sections, say if we cut off sections of the maximal domain of one by the other, so we institute some sort of cutoff function. What we need to know is that we're going to land in the maximal domain of the other operator, right? The other operator could do something really funky, and we might not be in the maximal domain of the other operator when we do that. So we can certainly independently study the cylindrical problem and this problem, but the way that we are doing things, the geometry is really contained in the operators themselves. And then we want to basically perturb from one operator to another. So what we need to know is that these operators are relatively bounded. If you have some sort of relative boundedness of the operators, then we, at least for some small part of the cylinder here, I mean, we just need to know it arbitrarily close to this part, we have that the restriction of the operator, so we would have things like compactly supported sections being dense in the domain, so multiplying by cutoff functions is not a problem, but then we need to know that the restriction of these two operators to this very small neighborhood we can equate the domains of the operators, right? So that's really a relative boundedness statement. And that's really what's required if we want to, arrive at a conclusion like the check spaces being equal. So that's the technicality there. Well, what I'm saying is that I am ignorant of the higher order case when it's non-compact. And actually, the non-compactness of the manifold is related to this, because if we could reduce down to a cylindrical thing like this, then we can also just study non-compact problems, right? What I'm saying is I can tell you with certainty that this is perfectly kosher in the first order case, and I'm pleading to ignorance for higher order because I haven't really thought about it. Yeah, I mean, a lot of the things that are coming from Melrose is really also very much connected to all of this. Yes, I mean, in some sense, you could do that, so here the setup is also a little different, because ideally, what we would really like is a operator on the boundary to somehow give us a nice operator d nu that allows us to understand a more complicated operator, right? So in the situation that we will see, particularly leading into the Atiyah-Patodi-Singer index theorem, the operator A really plays a crucial role. So it's really the operator on the boundary that really plays the role, right? And that I can tell you with certainty in the first order case. And we will really work through that quite carefully in the first order case. And maybe then, if you're interested, you can think about how that picture would look in general order. Okay, so maybe I'll stop there. Thanks for your attention again, and see you next Monday.